Alright, so greetings, welcome to week 9. Today we'll be discussing two questions, and the first question in front of us is about frequency response. So let's get started. So in this first question, we are considering two transfer functions P1 and P2. For each transfer function, we have to find the respective corner frequencies in radian per second. Then we have to find the magnitude of the sinusoidal transfer function as frequency tends to 0, and the phase in degrees of the sinusoidal transfer function at the respective corner frequencies. So for the first transfer function P1 of S, it's 2S plus 1. So to obtain frequency response, we substitute S is equals to j omega. So if we take uh, the magnitude of this, then it will be 1 over square root of 4 omega square plus 1. So if we want to find corner frequencies, that would be the intersection of the low frequency component and the high frequency component. So you can take, when omega tends to 0, modulus of the magnitude of E of j omega tends to 1. And when omega is a large value, then what we can do, we can neglect 1 against 4 omega square. So when omega is large, we can write the magnitude as 1 by square root of 4 omega square, that is 1 by 2 omega. Corner frequency is intersection of low and high frequency asymptotes. So if we want to find intersection between the low frequency and the high frequency components, then we can equate them. So 1 over 2 omega equals to 1. That means omega equals to half radian per second. This is the corner frequency. Similarly, let's take a look at P2 of S, which is 2S plus 4. So if we substitute j omega, in place of s. So that is s equals to j omega. So p2 of j omega would be 2 into j omega plus 4. You can take 2 common here. If we take the magnitude, so 2 will remain as it is, and we have omega square plus 4. So to obtain the low frequency asymptote, we take omega tending to 0, the magnitude of 2 square root 4, that is 2. Oh, sorry, yeah, 2 into 2, that would be 4. And to obtain the high frequency asymptote, we take omega to be very large. This implies we can say that omega square is much bigger than 4. So in this situation, the magnitude of this would be 2 into omega. So at the corner frequency, these two would intersect. That means 2 omega c, where omega c is the corner frequency, would equal to 4. So this is the high frequency portion, this is the low frequency asymptote. This implies omega c is 2 radian per second. So we have found the corner frequencies in both the cases. Now we want to find the magnitude in decibel as omega tends to 0. So let's continue this. So magnitude B part. So P1 of j omega, the magnitude is 1 over 4 into omega square plus 1. And we just saw as omega tends to 0, or rather we want to find, yes. So we have to find the magnitude of the sinusoidal transfer function as frequency tends to 0. So as omega tends to 0, this would be 1. So if we were to convert this in decibels, is equal to 20 log whatever the magnitude we have found out here, which is 1. So this would be 0 decibels. So the magnitude we have found out for P of P2 was 2 under root omega square plus 4. When omega tends to 0, was 4. So if we were to write this in decibels, the magnitude of P2 is 20 log 4. So this would be 12 decibels. So what we can see from here is that when a constant signal is given to this transfer function given here, we will not see any kind of DC amplification. Whereas if it is given here, we would see the gain of 12 decibels for the second transfer function, that is P2. Now coming to the third portion, find the phase in degrees of the sinusoidal transfer function at the respective corner frequencies. So in part A, we have found out corner frequencies as this one, where omega c was half for the first transfer function P1, and this, where the corner frequency was 2 radian per second. So for the C part, we have to find angle P1 of j omega. So this would be tan inverse of 0 over 1. So if we look at the transfer function P1, in numerator we do not have any j omega term, so that becomes 0 in the numerator of tan inverse, and there is 1 which is the constant one, so 0 by 1, and minus 2 omega by 1. So this would be tan inverse 0 minus tan inverse 2 omega. And when we put omega equals to half radian per second, this would be uh, tan inverse 1, that is 45 degrees. And since there is a minus sign here, that is minus 45 degrees. Similarly, angle of, so we have in the numerator, the transfer function is 2s plus 4. That would be, when we when we substitute j omega, we have 2j omega plus 4. So we'll have 2 omega in the numerator and 4 in the denominator. So at omega c equals to 2 radian per second, we get, so this is P2, angle of P2 into j omega is tan inverse 1, that is 45 degrees on the positive side. So we have found the phase of the sinusoidal transfer function as at the corner frequencies for both the given transfer functions. Now let's move on to the second problem for today. We have a plant whose transfer function is given as 1 over s square plus we have transfer function as 1 over s square plus 3s plus 9, and we have to find the following things. We have to find the magnitude of we have to find the magnitude in decibels of the low frequency asymptotes, and in the magnitude plot, and we have to find the corresponding transfer function. Then we would find the corner frequency as well as resonant frequency. So yeah, let's go through this. The transfer function given is E of s is equals to 1 over s square plus 3s plus 9. So if we substitute s is equals to j omega, we would get p of j omega to be 1 over j omega square. So that is minus omega square plus 3j omega plus 9. That is the frequency response function. And if we take the magnitude, this would be the p of j omega. Let's so we have 3 into omega whole square plus 9 minus omega square whole square. So now we have to find uh, the low frequency asymptote. So this low frequency is asymptote is found when omega tends to 0. So if we take this limit, we get 1 over 9. So if I were to find this in decibels, minus 19.1 decibels. Now we want to find the high frequencies. So what happens at high frequencies? Uh, Omega becomes large. So if we were, so say omega is large, and if we were to open this denominator here, this would be, so I will open this term first. That will be omega power 4 minus 18 omega square plus 81, and we'll have plus 9 omega square from here. So this would become omega power 4 minus 9 omega square plus 81. So when omega is a large value, in comparison with omega power 4, we can neglect these terms. So E of j omega would end up becoming 1 over omega square. So let's look at corner frequency. What is the corner frequency again? It is the intersection of low and high frequency asymptotes. So the high frequency asymptote was 1 over omega square, and the low frequency asymptote was 1 over 9. This means we have omega corner frequency of 3 radian per second. So now let's come to the third portion, that is resonant frequency. So this is the frequency at which the magnitude of the phase plot would peak. So we have this the given transfer function as 1 over 9 omega square plus 9 minus omega square whole square. So consider the term inside the square root as d of omega, which is 9 omega square plus 9 minus omega square whole square. So when would this magnitude peak out? It would be maximum when the d of omega term would be minimum. So if we differentiate this, d by d omega of d omega So we have 18 omega as the derivative of first term, and second term 2 will come out 9 minus omega square, and then we would differentiate the omega square term which carries a minus sign with it, and it will be 2 omega. So this is 18 omega minus 2 into 2, 4 omega in bracket 9 minus omega square. So uh, so oh, right. So if uh, we want this to be 0, so to obtain extremum, d uh, this derivative of d omega with respect to omega should be 0. This implies 4 omega square minus 18 omega to be 0. So we'll get one solution as omega equals to 0, and the other one which we are more interested in is omega equals to 2.12 radian per second. So this is the resonant frequency. So that's all the questions we have for today. Do you have any doubts to ask?
No, Paul, it's all clear.
All right, great. So I think we have some time in the session. If we are okay with it, let's look at some allied topics. Let's have some discussion on observability. Uh, we can bring in little bit elements of modern control if we do not have sufficient questions here. We are okay with it.
Yeah, yeah, sure. Go ahead.
All right, so let us have a new page. We'll have discussion on the state space representation and observability. So in last discussion, I think a week or so ago, we had a discussion on state space. So where we said that x dot of t is equals to a into x of t plus b into u of t. This was the state transition matrix. Sorry, state equation where a is the state transmission transition matrix and b is the input matrix. This is measurement equation. So what we can do, we are asking something about observability. So what is observability mean? We are asking ourselves a question that given a set of observations, can the initial state of the system be uniquely determined? So this is the question we are asking when we ask, is the system observable or not? So say you have different, you have say a set of n measurements, and if I may write the ex, uh, same state space representation in discrete form, just for ease of understanding, although the argument is exactly the same. So say we have y0, and for sake of simplicity, say uh, we can remove this term as well. So that effects can be accommodated at later stage, which after the derivation you would understand. Say y of 0 is c into x of 0, and then you have y of 1 to be c into x of 1, which is say c into a of x of 0 plus b into u of 0. So since the input was given by you, you know what the input is, and you have knowledge of b and c, which is your state and input and measurement matrix. You can take this term and subtract here.
Paul, one second.
Yes.
It's x dot of k plus 1.
No, it's x of k plus 1. We are writing it in discrete time.
So this A and B is
Different.
okay. It's a different set then.
Yeah. So let me denote the continuous ones by c.
Okay, fine. All right. Yeah.
Okay. So let's subtract this. So y1 minus cb u0 is equals to ca x naught. All right. So let's remember this term. And here, what I would say is this entire term, you write it as y tilde 1 is equals to c into a into x naught. So similarly, if you were to account for, similarly, we can write it y2 equals to c into a into x2. Sorry, c into x of 2. So a into x of 1 plus b into uh, u of 1. Now here we can substitute x of 1 using the discrete time equation as y of 2 is equals to c into, so if I were to take this input terms again, which is known to me, and move it on the other side, you can define y tilde of 2 as y2 minus CABU of 0 minus CBU of 1. So y tilde of 2 would be CA square x naught. So let us, if we come back here and define y of 0 equals to y tilde of 0, which is C of x naught. So this is the first equation, this is another equation, and this is another equation. So you can always write y tilde n is equals to c a power n x naught. Uh, are you fine with this?
Yeah, yeah. But what is the significance of y tilde n? How is it useful? Because
What is
inside
the,
that there are a lot of terms which vary, right?
yeah, but all the terms. So what we are trying to ask is, given a set of observations, okay, and of course inputs, can the initial state of the system be uniquely determined? Okay, so yeah, so you can see lot of computations. Mm, but is this form acceptable, that y tilde n equals to c a power n x naught?
Yeah, yeah.
All right, so can you repeat your question?
Um, like I don't understand why. Like, what is the significance of y tilde n there? Like, there are a lot of terms within y tilde n which we are not considering, right?
No, we are considering, no, we are using them. So see, you get a measurement at say y2, you have received a measurement,
Ah,
and you already know what input you had given at time 0 and time 1. So y tilde 2 is also a constant, right?
yeah, yeah, yeah.
Which can be computed. What is our unknown here? The initial state,
Initial state. Okay, yeah.
right? So if I were to write a matrix equation,
Hmm.
so where you have y0, y tilde 0, y tilde 1, y tilde 2, and so on up to y tilde n. So now Although we did not consider this d of uk term, you can also club that d of uk term into this y tilde, right?
Yeah, yeah, yeah.
So we have this vector now. So we have cx naught. All right. So we have this equation. So if we were to take this x naught as a separate entity, we'll get a matrix C, CA, CA square, and so on up to CA power n into x naught, right? So this is of the form, say, capital phi, or let's denote this as O into x naught. This is as, say, capital Y. So if your O is full rank, then x naught can be uniquely determined. All right.
Wait. If O is full rank, do you mean each term in O
No,
matrix?
no, no. O is full rank means O is invertible. That means determinant of O
But O is one
is not 0.
dimensional.
O is this matrix C, CA, CA square, and so on.
Yeah, so it's one dimensional, no?
Oh, no, no, it's not. Let's try a small example maybe. So, so say you have x1, x2. Okay, this is your A. All right. So this is the expression. So observability matrix here would be C and CA. Okay. So it's you, how much ever states you have here, in this case 2, you go up to n. So C was what? 1 and 1. And CA, if we were to do 0.8. So we get 0.5 and 0.8. Okay. So if we were to take determinant of this, that will be 0.8 minus 0.5. That is 0.3, which is not 0. That means O is invertible. Implies you can uniquely determine the initial states, and if you know x naught and x1 naught and x2 naught, and you know the inputs, you can propagate all other steps, right? So you can figure out the entire evolution of x. Okay. uh, is this clear?
Yeah, yeah.
All right, so that's one small discussion on observability I thought I would go. So if your system is observable, you can try to check things. I mean, it becomes easy for you to estimate the then this observability notion can be brought into ideas like uh, filtering and so on. If you have a fully observable system, then you can essentially do correction in all your states. But anyway, that's discussion for some other day. So do you have any questions on this?
No, no, no.
All right, great. Thank you for joining today's class.
Thank you.
Thank you.